Truckloads of banana stems roll in like green logs, but this isn't produce processing. It's a materials plant built around one idea. The banana plant is harvested once, and the trunk it leaves behind is mostly water, mostly cellulose, and usually treated as waste. In a high-tech banana stem factory, that waste becomes fiber for textiles and composites, pulp for paper, and biomass for energy using a tightly controlled industrial workflow that has to move fast before the plant tissue starts to break down. The stem is technically a stem, made from tightly layered leaf sheaths, and it behaves like a wet composite. Long cellulose bundles embedded in pithy tissue with natural gums and lignin-like binders. Fresh stems can be over 80% moisture. So the entire factory is designed to separate valuable solids from water efficiently, without shredding the fibers into short, low-grade fragments. That's why the line starts with precision cutting. It's not brute force grinding. At receiving, stems are weighed, scanned, and graded. Vision systems and moisture probes help sort by diameter and maturity because fiber length, fineness, and strength vary with cultivar and growth conditions. The goal is consistent feedstock for machines that run best at steady load. Automated cranes or fork systems place stems onto in-feed conveyors. Where rotary knives trim them to a standard length to match the decorticators downstream. Metal detectors and stone traps protect the rollers, because one embedded staple or rock can scar a set of hardened extraction drums and ruin fiber quality for hours. Next comes splitting and flattening. A banana stem is layered like an onion, and those layers matter. Splitting blades open it into manageable slabs. Then compression rollers squeeze out free water before the fiber is even exposed. That early dewatering is not just for cleanliness. It reduces the hydraulic burden on washing and wastewater treatment, and it lowers the energy required for final drying. The core machine in most modern plants is a continuous decorticator line. Think of it as controlled mechanical peeling, serrated feed rollers. Pull each slab forward while a rapidly rotating beater drum and scraper plates strip away the soft pith. The trick is pressure control. Too gentle, and pith stays attached and stains the fiber. Too aggressive, and the fiber bundles get cut. Reducing the average staple length and downgrading it from spinnable, textile fiber to filler grade. That's why high-end lines use servo-controlled nip rollers and load cells that adjust clamping force in real time, reacting to thickness changes every few centimeters as the fibers emerge. They're still loaded with sap and gummy compounds. Immediate washing is essential. High-pressure spray bars and countercurrent wash tanks remove sugars and fine pith particles. Now, vibrating screens separate long fibers from short fines. Some facilities add enzymatic pretreatment in warm wash stages to loosen natural binders without harsh chemicals, aiming to improve softness and dye uptake while reducing effluent load. Compared to strong alkali-only processes, the pith and wash slurry don't go to waste. Hydrocyclones and screw presses separate solids from liquid, producing a wet pith cake that can be routed into multiple product streams. In a pulp-focused plant, the cake feeds a continuous digester, where heat and controlled chemistry break it into paper-making pulp. In a composites-focused plant, the pith becomes a lightweight filler for boards, molded packaging, or biodegradable pots, often blended with starch-based binders. In an energy-integrated plant, pith and fines are anaerobically digested to biogas, or dried and pelletized as boiler fuel, turning what used to be disposal cost into process heat. Back on the fiber line, the washed fibers go through deguming. Banana fibers' feel and performance depend heavily on removing hemicellulose, pectin, and residual gums. Industrial deguming is a balancing act between cleanliness and tensile strength. Alkali baths, enzyme tanks, or hybrid systems run under tightly controlled temperature and pH, monitored by inline sensors. The best plants don't guess. They log conductivity, turbidity, and chemical dosing, and they link those parameters to lab-tested fiber strength results. so recipes can be optimized for each batch. After deguming, rinsing and neutralization prevent chemical carryover that can weaken fibers during storage. Then comes one of the biggest energy challenges in the entire facility: drying. Because the fibers start extremely wet, drying strategy determines operating cost. High-tech plants use staged drying mechanical dewatering first through squeeze rollers or belt presses. Then thermal drying using conveyor dryers, heat pump dehumidifiers, or waste heat recovery from boilers. Moisture sensors at dryer exits keep fibers within a target range, because over-drying makes fibers brittle and increases breakage during carding, while under-drying invites microbial growth and odor. Once dry, the fibers are opened and aligned. Bale breakers loosen compressed bundles, then carding machines comb them into parallel strands. Removing remaining shives and short fragments. Air classifiers separate by fineness and length, producing different grades: long, cleaner fiber for yarn, mid-grade for non-wovens, and short fiber for reinforcement in injection-molded bioplastics. This grading is where high-tech becomes visible in data. Optical inspection systems can quantify color and contamination, while tensile testers and micro-nair-style fineness tests verify whether a batch meets textile or industrial specs. If the factory makes yarn, the aligned sliver goes to drawing frames and spinning. Banana fiber is stiffer than cotton and behaves differently under twist. So many operations blend it with cotton, viscose, or recycled polyester to tune strength, softness, and machine runability. Spinning rooms run under controlled humidity because electrostatic charge and brittleness can spike waste rates. Every break is logged, and modern systems correlate break frequency to fiber moisture, fineness, and deguming conditions, turning the factory into a feedback loop rather than a one-way process. If the goal is non-woven materials, fibers feed needle punch or hydro entanglement lines. Needle punch mechanically interlocks fibers into felt-like sheets for insulation, geotextiles, and automotive panels. Hydroentanglement uses high-pressure water jets to tangle fibers without binders, creating a cleaner, more recyclable sheet, while demanding advanced water filtration and recirculation to stay economical. In composite sheet production, fibers are laid and impregnated with bioresins or thermoplastics, then hot-pressed into boards that replace wood-based panels and reduce reliance on formaldehyde-based adhesives. Asterisk throughout the plant, water is a central engineering problem. Washing and processing can consume large volumes if unmanaged. So, the largest facilities operate closed-loop water systems. Settling tanks remove grit. Dissolved air flotation pulls out fine organics, and membrane filtration polishes water for reuse. Sludge becomes feedstock for composting, pellet fuel, or biogas digestion. This isn't just sustainability messaging, it's operational stability, because consistent water quality keeps washing performance and chemical dosing predictable. Quality control runs in parallel with production. Fiber strength is measured on universal testing machines. Elongation and modulus are tracked for composites customers. And color is monitored because browning can indicate overprocessing or microbial activity. Residual gum content matters for dyeing and softness, so labs run standardized extraction tests. Even odor is managed, because sap-rich biomass can ferment quickly. Ventilation design, rapid processing, and controlled storage are as important as any single machine. The reason a banana stem factory can be largest and high-tech at the same time is scale paired with logistics. Banana cultivation is continuous in many regions, creating a steady stream of pseudostems after harvest. To capture value, the plant must be close enough to farms to process material quickly, and automated enough to handle huge volume with minimal manual sorting. When that works, the yield math becomes compelling. Only a small percentage of a fresh stem becomes long fiber. But the remaining mass is not waste if the facility is designed as a multi-output biorefinery. What looks like a pile of wet agricultural residue at the gate becomes several controlled product streams at the dock. Graded fiber bales, rolled nonwoven sheets, pulp pellets, and sometimes even biogas-generated electricity, feeding the very motors that run the decorticators. The uniqueness isn't a single miracle machine. It's the integration mechanical separation tuned for fiber integrity. Chemical or enzymatic treatment tuned for performance. Drying tuned for energy efficiency. And recovery systems tuned so nearly every part of the banana stem exits. The building is a sellable material instead of a disposal problem,